Like I say, just try to be careful. If I smash it, that's it.
Couple of things, some class business. You know what I can do is, if you're struggling to finish this homework, which I don't care for, but whatever, I can wait till 5 to post the answers. It's giving you that bit of an extra hour to come give me the homework. Oops, sorry. Can you get the door? So yeah, I can wait till post the answers till 5, so you can come by my office. I'll probably be in my office. At 5 I have a meeting, so it won't be there, that's it. What else? Remember, you have the option, just wait till the class. You have the option, if you get in an accident or something, this does happen a lot, car breaks down, you can photograph it, all right? So just make certain that I can read it. I just want to make sure that the answers aren't changed. So if you have a problem, you can't make it, photograph it with your all of you got iPhones like that. Photograph it, send it to me. Now, I don't want my TAs to grade that. They hate it when you do that to them. It's just a placeholder. As long as I can see the answers and that, to be blunt, we haven't changed them. Or, as long as I can see I haven't changed them, then I'm totally fine with that. But I don't like my graders trying to grade off your photograph. It's very difficult for them. They hate doing that. So it's just a placeholder. You come by Friday and give me the thing, because they usually grade on weekends. Okay, Wednesday next, I'll return the stack. We're generally pretty good about doing it within a week. Sometimes we screw up. What I'm going to do is at the end of the class, alphabetical, A's to Z's, I'm just going to spread them here and give you a couple minutes to come pick them up. So, anyway, that's just how I distribute them. It's not it gets very chaotic. There's actually over 100 of them now. It gets chaotic, but it concerns me if you don't ever pick up your homework. That's kind of a bad sign that, you don't even know what you got right, what you did. And I swear to you, the tests are the same as this thing right here. So, except one difference, they're easier. Number 2, don't need to get bitchy. Last Friday, you guys were talking way too much. I had a lot of complaints as well as my own complaints. I cannot do that. All right? You guys were talking so much, I couldn't hear myself think. But remember, I'm about a quarter deaf. Not deaf by a quarter deaf, 1 minus support. And it means that I am sensitive to sound. Human behavior is never what you think it is, right? I should be less sensitive. I'm not. Because what little I can hear, if it's from you, I can't hear myself. I cannot do that. Now, folks, I had to threaten to expel one person once from my class. I don't want to do that again. So don't make it, all right? It really did get on my nerves a little bit, and I don't want to start this class screwed up, because I swear to God, there was this, I don't know if I told you, the second time I taught this class, I learned to do this, because I had these 4 engineers, and these four guys, called them the 4 little crows, and they talked the entire time. And because I did not nip it in the bud, like now, they did it the whole time, I lost control of them. And I never gained control, so I'm doing that now. So pretty pleased. And then I had 4 or 5 complaints saying I couldn't hear it. So I will not put up with that at all. So I'm sorry to be bitchy, but I just want this to go well, especially there's so many of you. I've never had so many students in my life. So, okay, I'm done complaining, but don't make me complain again. All right, so the next homework, I am almost done with it. I'll have it up by 5. I just have to write 2 more questions. I'm sorry, I tried to get it done right before class for this one time idiot. I posted the homework an hour before class. This guy starts on it an hour before class, and he goes to problem set 4 when we were doing 3, and he spent an hour trying to do a problem set on materials I hadn't covered. Okay, that was stupid, but anyway. So I always post them after the class, but I'm not quite done writing it yet. And again, I know I harp on this too much, but for those of you who have last year's materials, The syllabus has changed heavily due to requests from the other faculty. I'm not tracking my last class last semester, nor any other semester. I've made a major curriculum change, just FYI. Again, I cannot emphasize, a lot of you have already asked me, oh, can we get practice tests? No. You can. You can get them on Coopers, you can get them from your friends last semester. But I swear to you, and I know I've already said this, but it bears repeating, you will give me last year's answer. It happens every time. You're going to get no credit for that. Now, you might say that's cheating. I won't go that far. Besides, you just screwed yourself. You got no points. So there you go. There's your punishment. Again, I know it's something to say, oh, but I want to see your previous test. Well, I'm going to tell you what's on the test. And I change every year. And I change the questions. And I know you may be thinking, well, it's just practice. I won't let that get in my head. Oh, yes, you will. Because I've seen it happen every time. So again, you got to sit back and trust me a little bit here, that every time I do this class, I change something. And I respond to you. I respond to your strengths. And I hit you over the head on your weaknesses, but not often. Like there was one class, I think my first class, Hess's Law, remember A, B goes to C, and then C goes to D, and so all that stuff you did in high school? I had a class that could not do it. They absolutely choked violently on their own tongue when it came to Hess's Law. I asked them a couple of questions. I saw they couldn't answer them. I backed off. It wasn't on the final. It was on the third test, but it wasn't on the final because I just see that they couldn't do it. So I just was like, well, what's the point? If this is just something they just can't do, I don't see any point in asking it because they just don't seem like they're going to figure it out. So I back off. You guys, if you do well in it, well, you're going to get more of them. All right, so anyway, that's how I'm going to operate. So again, just trust me on this. So, okay, I'm talking too much as usual, and we want to go over actual material. And again, I always review what we did last time. I found when I had this class, the one guy I had, he did that, and it was just shockingly useful. And okay, we talked about the virial equation of state. I'm not going to write it up again. Your homework is actually half virial equation of state. Your homework is going to be half what I covered today. And so anyway, so today is kind of important for the next homework. I'm also going to go over. See, I've got this down pat. I don't have those in my notes anymore. So we did the virial equation of state to talk about real gas versus perfect gas properties. I did base the homework on the virial equation almost exclusively. Just manipulations we will do today. The manipulations we will do today will very likely be on the first test, and it will probably be one of the harder questions. Remember, I go easy, harder, harder, hardest. It will be probably the hardest section. I'm not committed to that, but that's what I'm thinking. Okay, if pressure was very large, then we found that Vm was equal to V, and therefore I assumed that the volume of a molecule, and I know pressure is very high in kind of solids, and the volume that's there, the volumes of the molecules or atoms, in the case of xenon or whatnot. And so I associate V as the finite volume of a gas, and that's something you're going to be working on for this next homework. Okay, so we had P minus ideal pressure, ideal gas law. Actually, I'd like to put it this way, and that was minus A over Vm squared. And this means that the pressure of a real gas is generally less than that of a perfect gas. And that, therefore, I assume that A has something to do with molecular interactions. Again, like how a galaxy will hold itself together by its gravitational attraction. Well, this is dipole-induced dipole attraction, sure, whatever. It's not gravity, obviously. Gravity doesn't really play a role in chemistry. It's a force that we always ignore. Sorry, getting cosmological again, I do that. And it has weird, it's hard to see this one actually because the units are kind of strange. It has to have units of pressure. It must be pressure. Therefore, it's pressure times liters per mole squared. Liters squared per mole squared, because that kills off this and returns pressure. Now, it's hard for me to see that that is an intermolecular force. Intramolecular force. It's hard to see that, but that is what it is. Okay, and A's and B's are always positive. And then, so other things I wanted to show you. I ran out of time. I am a little bit behind right now on the schedule. I can already tell. I'm going to be a little bit behind, so I do have to, I think I told you that last time, I do need to talk kind of quickly. So let's look at various gases like helium. I'm sorry, it's bigger. It's a big room. Helium, this is 0.024. And as I mentioned before, liters per mole, it's not like it's miles cubed per mole. That would be a very large number. Liters is not such a big thing, not a big volume. And these are small numbers for kind of small volumes, krypton, so obviously I'm looking at the perfect gases. 40, and acetylene. A rather large gas molecule, if you think about it, it's not that easy to get things in the gas phase. A lot of things decompose before you can ever vaporize them to a gas. Actually, most things do. So a lot of things you can't get into the gas phase. The important thing is that you learned in freshman, I'm going down the periodic table, you knew that the size of a molecule gets bigger as you go down the periodic table, with like francium being the one thing that doesn't do it because of quantum mechanics. But anyway, obviously the numbers get bigger. Your homework, first question. I'm going to ask you about the size of, actually, xenon. So I don't have xenon on here. I talked about xenon, its B parameter, and its actual size. I'm going to have you compare the two. It's a units question, because this is going to be in liters per mole. I give you the radius in picometers, and you have to compare them. Obviously, you're going to convert the picometers. It's a radius, turn it to a volume, and multiply by a mole. I just gave you the answer, by the way. There you go. Then you can compare it to B. They won't quite be the same. Regardless. All right, let's do another one. Let's look at A. I'm going to draw a graph. And A is in bars. Sorry, A, and that's in bar. Bar liters squared mole squared. Okay, now you may have noticed that A on your homework, A is difficult to work with because I always like to work with kilopascals and liters when I do gas equations. It's not standard SI. A bar is not SI. That's an American meter, which sucks. And so the reason I did that, instead of giving it to you A in kilopascals, you just have to multiply it by 100. The reason I did that is because that's what I found online. And again, anything you have you can find online is fair game. Actually, when I teach 346, when you do the real hard quantum and you do those integrals, no more derivatives, integrals, I actually have people do it on the Wolfram, the Mathematica website. I'll let you do it because I don't care. It's there. We should use it. But I don't know who's teaching. We haven't figured out who's teaching 346 yet. It may be me. I don't know. We usually switch up teachers between 346 and 342. And it's weird why we do that. I think it's actually might be a bad idea. But anyway, I just believe in the technology we have. You know, if you don't want to write all this down, it's not going to come up again. I just want to point out to you that in this class, a good thing about this class, you can use your instincts. You can't in quantum. That sucks. It's just the nature of the business. Quantum is such a weird thing. And that's why we had a hard time understanding it. There is no observable quantum mechanical principles without some giant machine that's very complicated and you have to have a PhD to work it. And I can see a car drives down the street. I can see that, but that's not quantum. That doesn't apply. So when it comes to my class, you can often use your instincts to understand this trend. And I'm going to talk about that in a minute. But when you do 346, just warning you, I'm not going to do a lot about this. Your solutions will be like 1 or 0 or a length. And it's just like, okay, whatever. So the hydrogen atom is about a Bohr big. And it's just not going to make a lot of sense because we just don't live in that world. But in this class you can. I can put this on a test and say, explain why. And you should know that helium is like a little rock. They don't interact with each other. They have this nucleus of only 2 electrons. Those 2 electrons are in the 1s orbital. They are not shielding each other. Right? So that makes this not very polarizable. When you add electrons to other orbitals, they get further away and they get shielded by those other electrons. So it gets puffy. It's puffy like Huffy. So you can see the interactions increase. Water, now you knew this as freshmen. You should have learned it in high school. In hydrogen bonds. It loves a hydrogen bond. It's got those extra electrons just sitting on top of oxygen like Mickey Mouse ears. Water loves to interact with itself. And so, of course, it has a very, very large A coefficient. So again, with those Loose electrons, because those electrons are further away, they're more shielded. Okay, so they get bigger, but those loose electrons are more polarizable, and they become more sticky. And you should kind of feel that. And you know water loves to stick to itself. Very strong interactions with hydrogen bonding. These guys don't hydrogen bond. So the trends make sense, and you know it from stuff we learned in freshman. Last bit, before we do something actually kind of complicated, as opposed to this boring P equals nRT crap. Here, I hate to just draw data, but because I don't PowerPoint, I have to sometimes. Let's look at the melting temp. Now remember that we get these A and B parameters, they're not temperature dependent. Why do I always do this to myself? All right. We get these A and B parameters by fitting data. And I'm not going to have you do that, I don't really care. Okay, 100, this is in Kelvin. 273. The A parameter is the A parameter, and what we get, we adjust Drew, helium, argon, krypton, so we'll just right about 100, and water. Yeah, melting 273, right? That was boiling. Okay, now, no fooling. It's on a perfect line. It absolutely makes sense. And you know, again, your instincts tell you, things that don't attract each other will melt at lower temperatures. Water, one of the most sticky liquids that exists, melts at a relatively high temperature. Think about all the solvents in organic, music organic lab. Those things freeze at really low temperature. Methanol. All those solvents, they freeze at really, really low temperatures. So they don't have strong interactions. And water is one of the highest liquids that melts. And again, it's a perfect line. So again, you see that the interactions of molecules are what make your A parameter what it is. And remember, the A parameter, for all things except helium and hydrogen, A parameter is generally dominant. And as you can see from here, they are definitely bigger numbers. Okay, now, here's the part that's on your homework. I guaranteed on the test and bloody likely on the final. This is a set of derivations that it's very traditional to know this stuff. Oh, you engineers, compression factors? Yeah. Engineers love compression factors. So we want to, the point of this is we want to make a measurement of how a real gas is different than a perfect gas. I want numbers, right? I want to get a sense of scale. And so how imperfect is my gas problem? And one way to do that is with a compression factor. Again, we have only a certain number of letters to call things. We call this one Z. And let's remember there's no little knot. That means this is the real volume, and that's the perfect gas volume. RT over P. And this will be van der Waals equation. And it is pretty much the same thing as the pressure versus the P equals nRT pressure. I exclusively work with this because ultimately the problems I want to analyze, this ends up being easier. I know we have pressures equal to all this stuff in van der Waals, but actually it is ultimately easier to do it this way, so I'm going to do it that way. It doesn't matter which way I put it, so I'm going to do it that way. And remember that this is going to come up a lot, is RT over P. All right, that's P equals nRT. Okay, so if Z is this, then I can say Z is equal to this thing, sorry I'm not working really well, which is Dm P over RT. And therefore, this is very simple, Z RT is, let me double check this, P RT, B would be, 1 over P RT. Let's see, so ZRT equals PD. One time I got this confused, PDO. Okay, so now what this ends up being, okay, PV equals nRT doesn't work very well. And your homework was actually one of the better extreme examples that I saw. It was way off, right? It was like 161 bar for methane under those conditions, and it's really 45 bar, which are real numbers. You see what this is doing? It's just fixing it. You do experiments, you figure out Z, and then you can fix your perfect gas equation. You can do it perfectly because you're going to base this on experimental numbers. So engineers love this. Instead of having to remember variable C and B parameters that are also temperature dependent, you can reduce it to one number. It's just better. Why wouldn't you think? So let me draw some more data. And I'm running out of room, so I will bring this forward now. Again, I don't like to draw data, but we don't have an option, and it's not in a PowerPoint, set in my ways. And this is the kind of thing, what I'm going over now, in the very beginning of the test, I have what's called true and false. So I make two statements in every question. One is true and one is false. And you have to tell me which one is false. I don't care about which one's true, why would I? And this is the kind of stuff that I will base it on, so just want to give you a heads up. Now, what are the units of Z? Exactly, right, exactly. And you can tell because RT is energy per mole and PPM is energy per mole, so Z has to be dead. Okay, so what's the compression factor of a perfect gas? I guess I made that obvious, didn't I? Okay, so perfect gas. Right, because if Z is 1, then this equation is P equals nRT. Okay, now what does this really look like? Now let's start with the weirdos. I'll just draw hydrogen. Oh, sorry, I hope I didn't mess up your graph there. I want to give you real numbers. And 200. And this again is in atmospheres. And I know I'm not doing this in pascals or kilopascals. It's just, again, this is what I found online. Okay, what am I doing? Hydrogen. Hydrogen compression factor is always above, I think it's, my guess is that it can be less than 1, but not that I found. I looked in some tables and I never saw one that was, I never saw conditions where hydrogen was below 1. Okay, this is like I forgot what temperature this is. Okay, then something like methane does like this. It does bend back up. That tends to be common. So this is below 1. And then of all the damnedest things, and I mentioned this to you last time, of all gases that is as perfect as a perfect gas, as a real gas can get, nitrogen's it. So back in the day when they discovered the absolute temperature scale and all this other stuff, they were using mostly nitrogen. They got the answers. It really helped. They got the right numbers for the most part. And of course they were refined, so we understand this stuff now. Okay, now I'm going to use this in a minute to try to figure out why some are greater than 1 and some are less than 1 and why some are balanced. And that's also part of your homework. Now here's an important one, and I've had this on test before, and that true or false statement. Z happens to be, unfortunately, temperature dependent. That kind of sucks. I mean, it is what it is. I mean, I'm not going to get angry over Mother Nature. I'm used to getting screwed over. And atmospheres again, and this will be for CO2. And again, if you don't really care to remember this, that's fine. I have added on the test that Z is temperature dependent. And so CO2 is a funny guy. That it's almost, you know, dry ice. Dry ice is pretty stable at room temperature. It does, of course, turn to gaseous CO2, but it's actually pretty, it lasts a long time. Solid CO2 is relatively stable for not really actually being a solid, but it's really temperature dependent. So 5. These are fairly extreme numbers, by the way. 0.2, this is relatively very strong effect. And so at 330, 0.7K, I found this. I think this is from your book. And at just a few degrees cooler, it does this. And you see that trend where Z tends to rise at higher pressures, tends to. It doesn't matter, that I won't hold you, so I don't really care. Okay, now the trends, why? And again, I'm seeing true and false questions right before my eyes constantly. Why is Z greater than 1? All right, well, I'm seeing my weirdo, hydrogen, and helium would be really right on top of it. I'm seeing my weirdo go above 1. I'm seeing a sticky molecule and a really sticky molecule. Our water's bad, CO2 is worse. Right? It's almost a solid at room temperature, and that's why there's such strong deviations from the perfect gas law. Okay, now I can tell, therefore, this is due to intramolecular forces. So if you don't mind if I abbreviate. And in case you had a little trouble, that's the A parameter. Of course, that's the A parameter that's doing that. By the way, we can calculate this stuff with van der Waals equation, which we're going to do. Okay, and let's see. So intermolecular forces, sorry, I kind of didn't do this right. Drive Z down. So I shouldn't have said this, sorry. Because again, Z is less than 1 is due to stronger molecular forces, because CO2 is the best example. Okay, now what drives Z up? Well, there's only really one example, 2 examples, hydrogen and helium. And again, we can look at the van der Waals equation, which we will do, and I can see that while the A parameter for hydrogen and helium are positive, right, they're not negative, they are positive, so they do interact with each other. They do have that induced dipole thing going on, but you can't really do that with 1s electrons. They just don't respond. They're too down to the nucleus. They're not going to move around the right way and polarize themselves. They're going to stay apolar because they're going to interact with the nucleus more than they interact with other electrons that just are whizzing by them. They just don't care. So hydrogen and helium having higher Z's, that means finite volume, which is B. Finite volume B drive Z sub. And again, so hydrogen helium's A parameter is weak, and if it's weak, then the B is going to take over. Normally, that's not the case. And they're the only gases that are known to do that. So, what else do I want to say? Okay, and the weird thing about nitrogen is that they actually tend to balance each other out. And again, that's a homework question. You're mathematically going to figure that out. So now what you can do is derive it. Okay, again, this kind of derivation almost will universally appear on at least the first test, and I usually have it on the final too. I got 2 derivations. Compression factor, I'll do that first, and then I'm going to do another measure of why is this gas not perfect, called the residual volume. And hopefully, we'll mostly finish up. So most of the homework, again, is based on today, and with a little bit on Friday. I'm going to start with the van der Waals equation, and then VM form. And these are algebraic, no calculus. And if you have a problem with algebra, I mean, that's not a lot I can do for you, in all honesty. So it's not hard. So I'm going to multiply by VM. So I'll put that, don't let your nose get confused. I'm just telling you what I'm doing. Is PVM is RTVM, VM minus B, minus A over V over VM. Okay. And then divide by RT. I don't think you folks can see, can you? If I go lower, can you see? Never mind. So then I'm going to, yeah, sorry, I already did it. PVM over RT is V, oh yeah, that's easy. Well, hey, wait, what am I talking about? I got it. Crap, I erased it. Yeah, this is, yeah, that P, P over RT is 1 over V on 9. So there, I've already gotten Z. See, this is relatively easy. And this is equal to Vm minus B times A RT Vm. There's not a lot I can really do with that. And there you go. Okay, that's it. I'm done. This is a two-step derivation. And I might have it on the test. The last two questions are always derivational questions. I'm sorry, this is about one of the easiest things I could have ever humanly asked. And so I can see that I have yin and yang. I see push and pull. This guy, as you're hopefully getting from the homework, because you're going to be getting a lot of this, always positive or always negative? Positive. Always positive. Is it always greater or less than 1? It'll always be greater than 1, because Vm minus B will always be less than Vm. Now, can Vm be less than B? Right? If it was less than B, it'd actually be negative. Vm is not ever going to be less than B, because remember, B is related to the size of the atom. And actually, it is a little bit off. And you're going to do that in your homework. The B parameter is about 10 times bigger than the actual volume. Like, we know how big a xenon atom is, and that's on your homework. We know how big it is. And B is about 10 times bigger. But then you're going to figure out why. That's because if you have to pack xenon into a box, there's space in between. And when you take that into account, the volume of the atoms plus the space that has to be in between them, because they're like little marbles, that will almost be exactly B. It's about half off. But anyway, it's very, very close. So you're not going to compress something beyond its size. And even if you did, you wouldn't have a gas, you'd have a solid. This isn't a solid equation, it's a gas equation, it doesn't apply. Although it is very close and sensible. Okay, A's, again, from regressions, from fitting data, A's just tend to be positive, even for hydrogen and helium. R positive, D positive, B positive. This is always pulling you down. So there you go. Now, what do you have on the homework? I have you do this for the virial equation of state. Now, I know I said I don't really care for the virial, but it's easy, and I'll have something like that very likely on the test. So, and how well does it work? Again, let me draw data. Z versus, oh crap, well, I have it right up there, but I'll redraw it. So I really try not to overwrite my own notes. Like do a derivation, on top of itself, because you can't really follow that. And so the real ones like this, trying to draw it like I did up there. Okay, and I've got it. Let's bring my pen, my colored pen. Okay, I take this equation, even though A and B are temperature independent, without van der Waals. Okay. It is shockingly close, and even for what? Oh, here we go. Sorry. Sorry, something just cut my throat. Even though it's, this looks like a relatively simple equation, it even follows the curvature like really well. It's not perfect because A and B are temperature independent. Again, the part of the homework lesson was that you saw that the perfect gas equation can be way off. Van der Waals is not perfect either, but it's a heck of a lot closer. And I think it's kind of amazing. It actually follows this weird curvature. I don't see that weird curvature. I don't see like a Taylor series, yet it's doing it anyway. So, anyway, okay, again, you have this on the homeworks. Another thing I'm going to do, you actually have to do this several times on your homework. And I will occasionally, like at the end of the course, I'll actually start asking these questions again to remind you of where we were at so that it helps you study for the final. Because I will bloody likely have this on the final. And I'm definitely having on the first test. And again, just see how simple that derivation was. The one on your homework is harder, a little bit harder, so you take one more step. But then the one on the the one on the first test will be easier. And what I do there, because you may be thinking that this is the 10th time I've taught this class, how many different questions can I ask? What I do is I make up a new equation of state. And that's why, as much as I said I don't care about the virial, I'm going to end up just making up an equation of state anyway. And so you just get used to it. And it just shows to me that, all right, so I'm going to do one thing. So I'll have a new equation of state on the test. You're going to give me compression factor, or what I'm about to do, residual volume. And then I will have you analyze what the result means, just like we just did. This drives it up, this drives it down. So that way I can also ask new questions every year. Okay, so this is a new subject. Residual volume. Okay, again, this is a lesson in how do I know that my gas is real versus ideal. And this one's kind of neat. Okay, if I have PV naught, and I'm calling it V naught because I have a PV equals RT, so that's the perfect gas law, then PVM naught over RT, again, this is 5th grade math, RT over RT is 1, sorry, and no units. Okay, 5th grade math. For a perfect gas, which don't exist, this is always true. Actually, one thing when I was designing the homework questions I found, well, I've known this for a while, almost all gases at room temperature and pressure, almost all of them, PV equals nRT, is accurate to within like 0.1%. It's kind of nuts. Most gases are actually pretty well behaved, especially nitrogen at room temperature pressure. But the reason that I went to an extreme, again, that was, I told you this before, that the conditions I found in engineering work for methane were actually about where methane condenses. That's because when we work with gases, when we drive the turbine, when we turn on our car engine, the gases are not remotely at room temperature or pressure. They're under extreme conditions. PV equals nRT doesn't work, so that's why I did that. I didn't want to have a question about real gases and show how well a perfect gas works, right? That's kind of not the point, and nor is it useful. Okay. Okay, again, this is for perfect. Right, this is important. For perfect gas. And again, you can tell by the nature of the equation itself that that's what's done with the perfect gas law. Okay, real gases. Real gases. Okay, atmospheric pressure is relatively low compared to the scale of things, especially to the pressure achieved inside of a power plant. It's much higher. So that gives you a lesson that we can say PVM over RT. Notice the lack of a little symbol is 1, but we're going to want the limit of relatively low pressures. Okay. For real gases, this tends to work, and it is actually pretty decently accurate. Okay, now here's the question that kind of blows people's minds. If this is true, so PVM and RT are pretty much the same. And here's the question. Is the limit of pressure goes to 0. There we go, sorry, OCD. PVM minus RT. This is a big question. Is that true? Yes, no. Any ideas? It says they're the same number here. They're the same number and I subtract them, shouldn't I get 0? So no? No, because you know I'm tricking you?
Yes.
Right? Now, it does seem immediately logical that yes, it ought to be 0. It is not. Here's an example. Make sure I get the numbers right. F is X, sorry, it's not so great today. And G is X plus 3. Now, the limit of X goes to infinity. Okay, I'm just showing you how these things don't, so this is a bit different. Of F over G is equal to 1, but no matter what limit, so it doesn't matter that I have 1 going to 0, 1 going to infinity. That's really irrelevant. F minus G is automatically equal to 2, no matter what X is equal to. So yes, this can happen, and it is not necessarily true that just because of this that you have that. And make this solid in your notes, put a mark. Don't write down something that's not right. Okay. So, God, here, I'll write this down and go to the other part of the board. Okay, residual volume. What am I doing? Residual. Okay, this is the definition. I didn't quite write it down right. This is the residual volume. I call it VRES. This is the limit, Professor. Hold on one second. Well, made a mistake.
Is the first one limit supposed to be 0, and the second one infinity?
Oh,
Or is it the other? Or is it both infinity?
no. This technically needs to go to infinity because I have infinity and infinity. And then this guy is going to 0. No, I've done it right. Yeah. Now again, I know this one goes to 0, this one goes to infinity. That really is irrelevant. I just want to show, it really wouldn't matter, would it? This is 1, but the same limit, okay, even though it's inverted, it really doesn't matter, is still finite. It just shows the principle is not correct. And also, I think I did mention this, why is this true? Well, if pressure is 0, then your volume is huge. You can't have one without the other, it's nonsense. So if the volume is huge and the pressure is 0, with a huge volume, these things don't hit each other. They never hit each other. Who cares about P? P doesn't do anything. Besides, the equation is Vm minus V. Vm is now gigantic. V is like 1/1000th of a percent. V doesn't matter. V ceases to exist. Low pressure, they don't interact with each other. They don't hit each other. They don't ever fly around each other and twist their orbits like, I brought up the analogy of like asteroids. So that's why this thing behaves, why real gas behaves perfectly. Okay, the definition. Definition is this. Vm minus Vm naught. Remember, it is residual volume, which is the limit. T goes to 0. Vm minus, now this one's important, RT over P. Because this is Vm naught. Now, all right, so I'm going to solve this guy. And this one, okay, folks, this one gets kind of complicated. This is, guys, right? This one gets complicated. And I will have this, I do have this on the homework. I do have this on the homework. I may have another test. I obviously like compression factors. This is a good 4 or 5 step process. And so every year, every semester, like in this case, I'm doing this semester to semester, I'll change the emphasis from residual volume to compression factor. And right now you got, well actually I did a little bit of both, but then I'll also change the equation of state to something I made up. And so that's how I kind of keep things fresh. And so that way if someone has old material, you're just really not helping yourselves because the questions are new. Even if I just change the number of moles, it's a different question. Okay, we're going to start here again. Don't forget when I ask these questions on a test, don't forget to take moles, take volume divided by moles. Okay. Now again, it's going to be kind of hard to follow. I'm just going to do these steps. And you're going to be like, where? Why? But at the end of the day, I get the right thing. All right, and that's why I'm doing the steps that I'm doing. And I'll tell you what I'm doing here, so in case you have trouble with your notes. P, Vm minus V, RT, minus A, Vm minus B. Whenever I screw this up, I often forget to multiply A times Vm minus B. That's a mistake I make. Okay, then I'm going to, okay, I hope your notes don't get confused, all right? You folks there can't see. Okay, I'm going to divide by P, so now I got Vm minus B. All right, so I'm slowly isolating Vm. I still have it on the right. Remember, I can't fix it. I can't fix the fact that I'm working to get Vm on the left, like here. but I'm not gonna be able to get rid of it on the right. Sorry, let me give myself some more room. VM minus B, and look at that, I got my RT over D. And I still have some, I'm gonna separate this, minus AVM over VM squared. I'll leave that for now, plus AB. P, sorry. Can't forget P, oh, sorry, let me rewrite this. P VM squared minus P VM squared. Okay, hopefully I didn't screw that up. Okay, now I'm going to bring this over here and bring that over there. Right, these are simple VM. And look at that, I got it. And you see, it was a little bit harder, but, I mean, really, it's just algebra. A over PDM plus AD over PDM squared. Okay, the hard part. The part that you may forget on the test. Here, I gotta do the limit. So, I should have done that already. Apply, I need to get this up. Apply the limit. Okay, we're doing good on time. Okay, now here's the thing. Our pressure's gonna go to 0. So what's gonna happen, so nothing happens here, what happens there? Pressure going to 0. It's going to what? Going up? Going to infinity? Okay, how does volume change? How did I lower the pressure? Increase the volume. Perfect gas law says that one goes up just as much as the other goes down. They might cancel. So which is it? Close. All right. So apply this limit. God, sorry. It goes to 0. R. I'm sorry. I've got it. Yep. Sorry. PDM over RT. I've already. No. It's right up there. All right. So we have to apply the limit as P goes to 0. No matter what, we have to do that because that's the definition. So the lim of VM minus VM naught. So you remember that that's what this is equal to B minus A. Now, so again, the problem is that pressure's going to 0, but volume has to go to infinity for me to drive the pressure to 0. But if I apply this, and I know this is going to sound cheap, I can replace PDM with RT because they are close together. I know that there was, I made a big deal of subtracting them and it not being 0, meaning that there is a slight difference, but it's not so great that I can't really substitute one for the other, at least in this step. Because it's how that they're, this is being divided by PDM, so I can divide it by RT. I'm not doing a subtraction. That's why I can do this mathematically. And what it shows you is that actually these guys balance each other. So it doesn't, one of them doesn't run away. One of them doesn't take over the other and go to 0. One of them doesn't take over the other and go to infinity, actually. No, they behave themselves. And by the way, I know you're aware, and this is going to come up when we do thermo, when I expand the gas, it likes to get cold, but I can let it warm back up. I can have pressure, volume, I can set it at any temperature. I have a flamethrower at home. You guys can talk and I'll bring it in. And so, I like to do it this evening. So no matter what, I can keep the temperature. You may think, oh, well, the temperature will go down when it's expanded. Yeah, well, let it warm back up. Now, here I got a problem. RT DM. Right? I took one of the DMs but I had another one left over. Now, that guy does what? This one will go to 0. There you go. B minus A over RT. Okay, okay, well, we will talk next time. All right, real quick, now this is what I'm going to have you do. All right, question 1 was on the exam, we're looking at the last 2 questions, which are kind of worth a lot of points, and I have given an equation of state, and part 1 is derive it. There you go. 3 steps, maybe 4, if I'm really feeling like a bastard. When you're writing an entire page, you're screwing it up. Stop. Go back, do some other questions and come back to it. You're screwing up. This is as bad as it gets, and this, yes, this was a little complicated, but this is as bad as it gets. All right, now you've done it. You freaked out, you went away from it, you answered some other questions, you got refreshed, you know that it's just a couple of steps, and then you get it. Question 2, well, part A. Part B, what's part B? Part B says why. Explain it. Part B will actually probably even give you the answer. You may have noticed I did that quite a bit. I'm going to keep doing that even on the test. So, it says to me that the volume of the gas molecules themselves increases the volume of the container. And why wouldn't it? It represents extra volume. You think that you're getting gas, I don't know, a liter of space. But when you shove something into it, it kind of added to that space. And this guy is lowering it. And that's, again, attractive interactions. That's the thing that makes a gas kind of want to compress on itself, lowering the pressure. Right? So of course, if the pressure wants to kind of be a little bit smaller, how would I do that? Well, maybe it probably would shrink the volume. Pressure is the reason that the balloon is as big as it is. But if the pressure goes down a bit, the balloon isn't going to be as big. All right? So up, down. And I value up and down quite a bit. And so A's, remember A's in most gases tend to dominate B's at most conditions. So that means that residual volumes tend to be negative. Also the answer to one of your questions on your present homework. These tend to be negative because A's tend to dominate. And, well, I guess, I don't know what else I'm talking about. Okay, so we'll finish up this stuff on Friday, and then Friday we'll get into the last bit of material you need for your problem set, so you can do your problem set over the weekend. If you have not turned in your problem set, I'll give you 1 more hour and that's it. So, if you haven't turned it in, come up right now and give it to me.
Did you look at solar